Okay, to the Lewis structures. So valence electrons are the most important ones in chemical bonding. They're the ones that are more on the outside of the atom, and they're the most loosely held. So we can write a Lewis symbol for an element, and we're just going to show the valence electrons as dots around the symbol for the element. So here we're going to write the Lewis symbol for oxygen. So we're going to start by the chemical symbol for oxygen, and we're going to look at the periodic table and figure out how many valence electrons does oxygen have? 6, because it's in group 6A. So we're going to be doing that a lot now. So we need 6 dots. 1, 2, 3, 4, 5, 6. So you could draw it like that. You could draw it like this. There's a bunch of different ways that you could draw it. But we don't want to do this. 1, 2, 3, 4, 5, 6. We don't want to just have them in circles. So this is not ideal. We're going to place these valence electrons to the right and to the left, and to the top and to the bottom. So north and south, east and west is where you can put the electrons. You can put the dots. And one of the reasons is that this makes it easier to count the dots without getting your finger out, right? It's like dice, right? When you have a die that has spots in that order, you just know it's 5. You don't have to count them. You ever played Monopoly with a young child that doesn't understand dice yet? They count all the spots. It takes forever.
Felt like I'm on there.
Yeah, been there, done that multiple times. Dots are placed so with a maximum of 2 on a side, and this helps us to visualize the number of them. So atoms that have 8 valence electrons are said to have an octet. So like if we look at neon, how many electrons, valence electrons does neon have? Neon, 8. Right? So 1, 2, 3, 4, 5, 6, 7, 8. North, south, east, west, all filled with 2. Right? So nice and symmetrical. And this is what all the other elements want. They want to get the 8 valence electrons. Of course, except for hydrogen and helium. Helium's little, and so it just has a duet of electrons, because that's all it can handle. But the octet rule says that atoms will transfer or share electrons to achieve an octet of valence electrons. So let's look at ionic bonds. Let's look at potassium and chlorine. So draw the Lewis symbols. So potassium is K, and how many valence electrons does potassium have? It has 1. Okay? Okay. Okay. Mm-hmm. Here's chlorine. How many does chlorine have? 7. 1, 2, 3, 4, 5, 6, 7. Both of these want 8. Metals are pretty willing to give up an electron. Non-metals are very willing to take an electron. So the chlorine's like, hey, give me that electron. The potassium's like, yeah, okay. So when that happens, now the potassium becomes an ion, and the chloride becomes an ion. And now they're like super attracted to each other. Ooh, you look good with 8 electrons. It looks like potassium's kind of left with nothing here, but there's that core underneath. So this is the electron configuration for potassium. It's got this 4s electron here, this 1 valence electron. When we get rid of that, when that one's gone, now the next level down becomes the highest floor on the hotel and likely to be taken away by the tornado? Well, there's 8 electrons in there. So by losing that one extra one, now potassium also has 8 valence electrons. So this made both of them very happy. Okay? We're not going to now draw 8 dots around this, because then that would be super confusing, because the way this is going to work is however many dots you had when you start, you're going to have the same number of dots in the end, because we're just looking at what were originally valence electrons. With all these dots in here, you can see how this negative sign might get mixed up in there. And so when we write a Lewis structure or a Lewis symbol for an ion, we usually put brackets around the element symbol with all the dots, and we'll put the charge on the outside. For this positive one, doesn't really matter. Okay, use Lewis symbols to predict the formula for the compound that forms between magnesium and nitrogen. Okay, so here's magnesium. How many valence electrons? 2. And we've got nitrogen. I like nitrogen to be blue. Here's nitrogen. How many valence electrons does nitrogen have? 5. So these are going to try to cooperate so that magnesium can lose all of its valence electrons and nitrogen can end up with 8. So nitrogen, being a nonmetal, wants to gain electrons, so it's like, hey, magnesium, I see you've got those 2 valence electrons, can I have them? Magnesium's, yeah, sure. So there goes one, and there goes another one. Now, magnesium has a charge, right? Because it lost 2 electrons. And nitrogen has a charge because it gained 2 electrons. Is magnesium happy?
No. Well, magnesium.
Magnesium's happy. Is nitrogen happy?
Mm-hmm.
Not quite. Well, what are they going to do? Well, if there is one magnesium atom around, there's probably like a gazillion others, literally, right? So let's look for another magnesium atom. So here's another magnesium atom. Also has 2 valence electrons. So nitrogen's like, I need one more. Hey, magnesium, give me one more. So this one happily gives up 1. Now the nitrogen is happy, right? This nitrogen now has a 3- charge. It's got 8 valence electrons. And this magnesium has a +1 charge. Is the magnesium happy? No. One of the things I like about Lewis model is you can make everybody happy with dots. It's great. Well, magnesium needs to get rid of an electron. Another magnesium atom isn't going to take it, so it needs to find a nitrogen. So here's another nitrogen atom with its 5 valence electrons. And so magnesium's like, could you take this, please? I just need to get rid of this 1 electron. Like, sure, I'd love that. Okay. They don't actually talk to each other, you know that, right? This reminds me of playing Hot Wheels with my boys. Cars always talk to each other, right? Okay, so now that second magnesium is happy. Is nitrogen happy? It's too bad. So this magnesium can give 1 electron, 2 electrons to the nitrogen. Now this nitrogen has a 3- charge. This has a 2+ charge. Nitrogen has 8 valence electrons. This one looks naked, but we understand that underneath there's a full valence shell with 8 electrons. Now everybody's got 8 electrons. 8 valence electrons. So how many of each did it take to achieve this? Well, it took 3 magnesiums and 2 nitrogens for the sharing, not the sharing, but the transferring of the electrons to work out. So Mg3N2 is the formula for the ionic compound that forms between magnesium and nitrogen. We learned how to do this a long time ago, right? Based on the charges. Well, +2 charge, -3 charge, and what combination do we need so that the charges can add up to 0? So this is just a different way of thinking about it. Any questions? Lattice energy, the rest of the story reminds me of Paul Harvey. So when ionic compounds form, that reaction is usually very exothermic. So when sodium reacts with chlorine to make sodium chloride, it gives off 411 kilojoules for every mole of sodium chloride that's formed. Well, where is all of this energy coming from? Well, now we know about ionization energy. So the sodium has to lose an electron, so that's going to cost 496 kilojoules per mole. That's the first ionization energy for sodium. And then the chlorine is going to gain that electron, so that's the electron affinity, so -349 kilojoules per mole. So we add those up, and we get +147. So this is predicting that when sodium and chlorine react, it's not going to give off 411 kilojoules, it's actually going to absorb 147. So something's wrong with how we're thinking about this. And what's missing is lattice energy. Lattice energy is the energy associated with the formation of a crystalline lattice of alternating cations and anions from gaseous ions. So let's look at a picture here real quick. So this is the idea. Here we've got all these ions in the gas state, and they're all attracted to each other. And so you could think of this as being a bunch of magnets, and they're all wanting to stick together. And so they're going to go, whoom, right? That's the sound they make, whoom, right? And when that happens, that releases a lot of energy because they all just went whoom and stuck together, right? So the potential energy gets lowered when these opposite charges come together. And the energy being lowered, where does the energy go? It's released as heat. So when we form ionic compounds, it's exothermic, not because the metal wants to lose electrons and the nonmetals want to gain electrons. I talk about it like that myself. But it's because when those ions come together, there's a huge release of energy, a lowering of the potential energy when the ions come together. So how can you measure lattice energy? Well, the simplest way is with the Born-Haber cycle. So this is going to take advantage of Hess's law. Yeah, chapter 7. Okay, so in a Born-Haber cycle, we've got a hypothetical series of steps. So when we were using Hess's law, we took equations where we knew delta H, and we combined them, so we added the equations together, and we added the delta H's together, and we got delta H for the reaction. Those were maybe real reactions. These are hypothetical reactions, but if we can put those together, then we can figure it out. So we use Hess's law, and we choose steps where the heat of formation is known. We also need to know the overall change in enthalpy, and then delta H lattice is the missing piece that we can solve for. So the sodium chloride forming, here's where we're starting with solid sodium and 1 mole of that and half a mole of chlorine gas. So we can imagine what's happening here is, well, we need to take solid sodium and put it into the gas state. That's going to cost some energy. People have studied that, and you can look that one up. Then we're going to form chlorine atoms from those chlorine molecules. So we can find out how much that is. And then we can take this sodium atom in the gas state and ionize it. That's the first ionization energy. So now we have sodium ions and chloride ions in the gas state, right? So when they come together and go, right? Oh, I'm sorry. I skipped a step. The shroom comes down here. This was chlorine atoms in the gas state. And when you make the chloride ions, then they release a little bit of energy. So it comes down a little bit. And here's the shroom. You got to do the hand motion. Shroom. Right? It comes together, releases a whole bunch of energy. So that's not how it happens, right? But we can imagine it happening that way. And the change in enthalpy is a state function, so it doesn't matter if this is how it happens or not. If we know the enthalpy change for this actual reaction, then we can calculate what this missing piece is, if we know all these other pieces. And then there are trends in lattice energy, and this has a lot to do with Coulomb's law. So here are the alkali metal chlorides, so lithium chloride, sodium chloride, etc. And the lattice energy for lithium chloride is more negative. It releases more energy than for, say, cesium chloride. So as we go down, the amount of lattice energy that is released is smaller. So why is this? Well, it has to do with how close these ions can get to each other. A lithium ion is smaller than a cesium ion, right? And so when we get this positive charge and negative charge together, Coulomb's law says that the force of attraction is proportional to 1 over the radius. The more pieces of paper you have under your fridge magnet, the less attraction the magnet has. You know, you get enough pieces of paper, it won't stick at all. So this has fewer pieces of paper, it's going to stick more tightly. This has more pieces of paper, they can't get as close, and so the energy that's released is less. We also see a trend based on ion charge. So here's sodium fluoride and calcium oxide. And the distance here is approximately same between these two. But sodium fluoride has a lattice energy of negative 910. Calcium oxide is negative 3,414. Well, the energy is proportional to the charges multiplied. So here, Q1 times Q2 is negative 1. Here, Q1 times Q2 is negative 4. And this is approximately 4 times larger. So lattice energies become less exothermic with increasing ionic radius and more exothermic with increasing magnitude. So then, oh, please let this be. No? Okay, there's only 2 slides left. We can do it. Predicting relative lattice energies. So, yeah, this is the kind of question that shows up on exams too. So, I'm sorry, but it does. So this is saying, arrange the following in order of increasing magnitude of lattice energy. So we got lithium bromide, potassium iodide, and calcium oxide. So let's look at where these guys are. So here are our cations. We have lithium and potassium and calcium. And our anions, we have bromide and iodide and oxide. And when you're given these compounds are chosen very carefully because you can't always predict this. Anyway, it has to be just right. So we're only going to give you the ones that are just right. So what we're looking at is the effective charge and the effective size. Charge is the biggest one, because if you have +2 and -2, the product is -4, which is 4 times +1 and -1. Right? So charge is the biggest one, and then size is the smaller one. So what we need to do is we need to look at the sizes here, but also the charges. So we've got lithium, bromide, so that's +1 and -1. We have potassium and iodide, +1 and -1. And we have calcium, 2+, and oxide is 2-. So which is going to have the greatest force of attraction between these ions based on charge? The calcium, right? So based on charge, this one's going to be like 4 times as big as those. So this is our big winner. Here we're going in order of increasing. So that tells us that the last one is calcium oxide. That's the biggest. And now we have to just decide between the other two. Well, lithium and bromide. So here's lithium and there's bromide versus potassium and iodide. Here's potassium and there's iodide. So iodide is bigger than bromide, and potassium is bigger than lithium. So potassium and iodide are kind of like wearing dinosaur blow-up suits, right? They just can't get very close to each other, right? And maybe lithium and bromide are just wearing regular Halloween costumes, I don't know. And so they can get closer to each other. So like with the paper and the magnet on the fridge, right? The more distance between them, the less attraction there is. So which of these has the smallest lattice energy? The ones that are the biggest or the ones that are the smallest? It's so many: bigger, smaller, larger, smaller. Whoa, 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 whoa. So these guys are bigger, and these guys are smaller. So who can get closer together? The smaller ones can get closer together. So they can get closer together, they're going to have a larger lattice energy than this one. So we put Ki here, and we put LIBR in there. So you're comparing charge and size. One more slide. Always good to ask, does our model fit with reality? Well, Ionic bonding model explains the high melting point of ionic compounds because the bonds here are non-directional. It's not just between two atoms. Those forces of attraction are in all directions. And so they're going to have high melting points. Non-conductivity of ionic solids. So solid table salt doesn't conduct electricity. In order to conduct electricity, you need to have charged particles that can move, right? The solid doesn't conduct. What about a solution of ionic compounds? Well, now the ions separate and they can move and they do conduct electricity. Turns out if you melt sodium chloride, it can also conduct